In our final video for chapter 2, we're going to take a look at symmetric matrices. Now, the connection of symmetric matrices to inverses and transposes is that a symmetric matrix is defined as when A is equal to its transpose. So say, for example, if I was to say S is equal to the matrix, let's just make something up, like 1, 2, 2, 5. Notice that if I transpose this, I get the same matrix because the diagonal would stay the same, so 1, 5, and swapping the diagonal entries 2 and 2, the cross-diagonal entries, we lead to the same matrix. And so notice that S is equal to S transpose. This by definition is symmetric. Anytime in mathematics when we're thinking about symmetry, we're talking about, at least for matrices, a reflection across that main diagonal, really similar to inverses, etc. So pretty self-explanatory now. The book will kind of get into when you're looking at an IJ entry for a matrix S, the idea is that this IJ entry, this row and column, is equal to the JI entry because of the transposition of the matrix. And so this is that definition. Now, in this video, trying to show a couple of examples, doing a little bit more of the math behind some of the examples that are given in the textbook, verifying when things are inverses, etc., and trying to back up in at least the 2x2 case of what you're seeing when you read through the notes and as you read through the textbook. But this is our key definition. I'm going to grab some water so my voice doesn't crack during the video. But we have our example, and luckily this example is actually the one from the text that you see given for the symmetric matrices. Now, not necessarily a trivial symmetric matrix, but another one that I want to mention is a diagonal matrix D, because we're going to see this a little bit later. A diagonal matrix is where we only have non-zero entries along the main diagonal, thus the name, super fancy, I know. Where, let's say this is 3 and this is, say, 5, then I would have 0 is 0 in a 2x2 case. And this would be the definition of a diagonal matrix. Now notice that if you transpose this is symmetric. The zeros would be the only thing swapping, which would be kind of important a little bit later on, but just something to identify. Now, one of the comments in the text gives that the inverse of a symmetric matrix is in and of itself symmetric. And so I thought it would be kind of nice to show this, and it just kind of gives another really basic case of how we determine inverses, specifically in the 2x2 scenario. Keep in mind, if you have a 3x3, if we're trying to find the inverse, we use elimination. You augment with the identity matrix on the other side. For us, in a 2x2 case, it gets a little bit simpler. Because if I am working with the matrix 1, 2, 2, 5, if I want to find the inverse for this, remember it requires finding the determinant in the 2x2 case. So 1 times 5 minus 2 times 2, so 1 over 1, which is really nice. And then we are swapping entries, so 2 and 2, and negating the diagonal, so -1 and -5. And so notice that when I do this multiplication, because these entries are the same, if I swap them for the inverse, then they're going to stay the same, which is, again, kind of the definition of symmetry. And so we get that the inverse for my S here, using this example, this is in and of itself symmetric. And so we have that if you want to do, this kind of tracks underneath, if you want to do the transpose of the inverse of a matrix, this is equal to S transpose of the inverse. These two statements are equivalent, which is then just the inverse of S, because the transpose is in and of itself the original matrix by definition. Just replace A with S there. And so this kind of helps hopefully verify a little bit underneath. What's really nice in terms of the diagonal matrix, and this is going to be something that will get highlighted a little bit more later on. In a diagonal matrix, it's even more clear because when you want to do the inverse, we are taking So in the example in the book, so I'll change it up a little bit from the example that I wrote earlier. The inverse for this matrix, being 1, 0, and then 1/10, he writes 0.1 in the text, but that's the reason why. Because when I multiply these two things together, it's going to give me the identity matrix. This 1/10 essentially coming from the determinant, because I would get 1/1, or essentially -1, -10, negating and then swapping and doing the inverse. So this is how we find the inverse when it's diagonal. We're just going through and dividing the entries in the main diagonal by their constants. Multiplicative inverse, I guess, is the best way to kind of think through it. But you can see that this is, again, symmetric by definition. The last thing here to really hit on, I think this is going to be the more important aspect, is symmetric products produce symmetry. So if I have a matrix that's A and it's equal to AT, if I just have a matrix A, and I multiply it with its transpose, so I do this kind of multiplication, this matrix will be symmetric. And it doesn't matter the order that you do this multiplication. If I take my transpose and do a left multiplication with it, this will still be a symmetric matrix. And you can kind of see, if you think about the entries themselves, how this would work. Because when you do the transpose, you're swapping those IJ entries. You have different entries being multiplied with the opposite or reflective side, creating the same number. And so when you do that, that's why you're going to see that symmetry kind of happen. For example, let's say that A is our matrix again. Let's make something up new. So we'll say this. So let's say we have a matrix A, 3, 4, and then let's just say 5, -1, just to kind of create something that's not just a straight sequence. If I want to find A transpose again, we're just swapping these entries here. So 3, -1, 4, and 5. And it's that swap again that's going to create the symmetry, because if I do this multiplication, A times its transpose, so 3, 4, 5, -1, multiplied with 3, 5, 4, -1. Notice 3 by 3, 4 by 4, that's going to give me a single entry, which again is fine in terms of the main diagonal. 9 and 16, so 25. Here, 15, -4, kind of keep that number in mind in terms of the operations. So 15 minus 4 is 11. Apologize about kind of the proximity there. And notice when I do the same multiplication here, 5 times 3, -1 times 4. It's mimicking that same one for the other entry. We get 11 again. And already we have symmetry, because as long as this is a non-zero, we're going to have a symmetric matrix. Even if this is 0, it's still symmetric. Doing that multiplication, 5 -1 by 5 -1, 25 plus 1 is 26. And so notice my result here is symmetric. And in the example that's given, notice that what we were working with here were two square matrices, a 2 by 2 and a 2 by 2, resulting in a 2 by 2 symmetric matrix. But it doesn't have to always be M is equal to N. You don't always have to have a square matrix to do this with. And so to show kind of what happens when M is not equal to N, so we're not doing a square matrix times a square matrix, kind of provides an interesting result. So following the example, he's got A is equal to, I believe it's a 2 by 3, so -1, 0, just kind of going by column, 1, -1, and 0, 1. This gives us the transpose. Instead of a 2 by 3, it's now going to be a 3 by 2. So -1, 0, 1, -1, and 0, 1 in terms of my flipping. Now, when I do this multiplication, if I'm going to do A times A transpose, kind of in the way that I've got it listed, I've got a 2 by 3 and then a 3 by 2. That result is a 2 by 2. You know, that's very different from if I was to do this times this, because that's going to create a 3 by 3. The matrix sizes are different. Now, again, the book kind of gives this, but just to help walk through that multiplication, if we're just following through with some dot products, row by column, -1, -1, plus 1 times 1, so 2. Then here, so 1, -1, so -1, which is really nice. and then dotting row with column, so that zeroes out that entry, so negative 1, 1 is negative 1, that zeroes out, so negative 1, notice the symmetry, and then this times this, positive 1 plus 1, so 2. Again, symmetric matrix. Which was the expectation, right? We've already talked about that when I multiply a matrix with the transpose that this is going to happen. I could have assumed then, once I found that that was negative 1, that's negative 1. Right, we have that. If we do A transpose times A, then again, because I'm reversing this order, it's 3 by 2 and then 2 by 3. That result is going to be a 3 by 3. We're going to have a different size matrix. So these two things aren't always going to be equal. And majority of the time, they're not going to be equal. So the order that we're multiplying a matrix with this transpose matters, because especially if it's m by n, so we have a rectangular matrix, the result will create a square matrix, but that square matrix isn't always the same in terms of dimensions. And that's because of the rectangular quality. We saw with the 2 by 2 earlier, I didn't show the other result, but even then, it may not always come out to be the same answer. To walk through and just kind of do this multiplication, this time we're doing 2 by 2 in terms of dot products. So negative 1, 0, negative 1, 0 is 1. Negative 1, 0 here is negative 1. Really just kind of keeping, negating the first entry, or first row there, 0. Second row, 1, negative 1. So we're just taking these two and subtracting, essentially row 1 to row 2. So negative 1 minus 0 is negative 1. 1 plus 1 is 2. Let's see, that's just minus 1. And then I'm just taking the final second row and repeating it because it's 0, 1. So 0, negative 1, 1. Just to kind of walk through this computation. So again, two very different size matrices, two very different results, but notice the symmetry. 1, 2, 1 is my main diagonal. Same entry, same entry, same entry. By definition, symmetric. I already kind of saw the same thing here. Now, why we care is that when I'm working with symmetric matrices, because those entries end up being the same, they help when it comes into elimination. Whether we're working with what's called a block matrix, which is what Dr. Strang shows at the bottom, or Dr. Strong shows at the bottom, which I'll leave as a challenge in terms of the video to take a look at. What I'm going to focus on is the beginning in terms of the taking the factorization that we've been working on in this chapter and how we can turn it into a triple factorization where you're going to see an interesting result in the middle of that factorization. So for example, let's say we took a matrix that's just a 2 by 2, and I'm going to use the matrix that he provides, so 1, 2, 2, 7, as an example. Now, if I go through and I take this matrix, which you'll notice is symmetric in and of itself, but if I wanted to take this matrix and factor it into the LU factorization. So again, I want to create this LU factorization. Remember that we get our U from doing the process Gaussian elimination and putting this into row echelon form. I want to zero out this entry here. So I zeroed out that entry by multiplying the top row by 2 and then subtracting from row 2. So I get my U is 1, 2, but then 0 and 7 minus 4 is 3. Now remember that my L comes from that factor that we're multiplying by. So the fact that I'm multiplying this first row by 2 means that in the 2, 1 entry, that's a 2 there. 1, 0, 1. Now notice that these two matrices that I have are not symmetric. Right? This is not symmetric, this is not symmetric. What's interesting is that if I focus on this matrix for U, I can break this matrix down into a diagonal matrix, which is symmetric, by only taking the main diagonal entries. So by saying 1, 3, 0, 0, in terms of that second matrix that we would need to get back to this one, this entry would remain a 0, but I would need 1s along the main diagonal to recover the main diagonal here. What's fascinating, and I would encourage you to try this to figure out why this entry is what it is, to get the 2 here, when I'm doing the multiplication, 1 0 times 1 0, 1 0 times what will get me back to here? Well, that's 2. In other words, this number is going to ultimately come here. Now, what's even more interesting is if I look at my overall factorization, remember this was my matrix for L. We're creating a new diagonal matrix here from the main diagonal in my upper triangular. This is L transpose. Notice that that other matrix that we're creating that's still upper triangular is the transpose of this. And we're creating then a triple factorization. We've taken this original matrix, which was S, that it was symmetric, and we've broken it down into this kind of factorization. And so this is what happens when it comes into symmetry and doing elimination and getting it into L and U. So if you start with a symmetric matrix, this factorization will always happen. We can always break down into this form, and we're going to have this kind of relationship at the end. The pivots are found in D. The matrix that would help recover U with that multiplication is the transpose there for L. If you take a look at the block matrix, it's the same thing. So what they end up doing is you are allowed to essentially divide a matrix up by quadrants, however you would want to. You create block matrices within, and you can perform multiplication just like you normally would do. And so you can kind of see how the factorization appears again, even if we block it off, taking a really large matrix and breaking it up into smaller kind of chunks. We would kind of create that same factorization. If there's questions around that, I'd be more than happy to answer that. And can focus on that a little bit more in detail if people are interested, but I think it's pretty clear in the text, and again, for the online class, you can see work in terms of the teaching notes. The last thing I want to kind of put up on the board, and this will finish us off for Unit 2, is the last line that he has, and it's a if-then kind of clause where if I know that S is invertible, then this is implying that A transpose A is invertible. And this works both ways. So by Verumbat, if I remember the wording right, probably butchered the way to say that, so I apologize since I also teach logic. Recall that S, a symmetric matrix, can be rewritten as the transpose of a matrix times the original matrix, because this will always create a symmetric matrix. That means any symmetric matrix could be broken down this way. So if S is invertible, then that means that this factorization would also have to be invertible. It would have to be. Now, if I know that this is invertible, then this is implying, in a two-way street, that AX cannot be 0 whenever X is not 0. The columns would have to be linearly independent. Right? There's no way to get 0 in any other case. Because of these two things being invertible, that would imply that when I find this inverse, A has an inverse. That means if A has an inverse, its columns are linearly independent. It is non-singular. So it's a really important kind of if-then, whether you're starting there, building out this to here, or going the other direction. In some of the practice problems for 2.4, you can use some of this information. Now, in terms of videos, if you're tracking the book and kind of using the YouTube as a way to, outside of Mount Vernon Online, I'm not going to get into 2.5. Again, I'm teaching this essentially as an idea or constructed towards high school level students who've completed multivariable, who've completed Calculus BC, and we're looking for another advanced math class. And so I'm going to leave off 2.5 and not get into derivatives and finite difference matrices. I encourage you to still check it out. I believe it's not crazy in terms of detail, and it does show a lot of application from Calculus, Cal 2 or a BC course into it. So I'd highly encourage, but if you're on Mount Vernon Online, we are skipping 2.5, which rounds us out for chapter 2. It means problem set 2 for your summative is available. You should be able to start working on that and then have that in. And chapter 3, we will start getting into the 4 fundamental subspaces and really starting to dig into not just solving these systems and talking about these solutions, but digging into column space, row space, null space, and then our final, looking at the other one, just the other vector spaces. I listed 3, but we've got the null space of A transpose. There's 2 null spaces that we're going to kind of consider. So that's where we're headed. We'll start getting into chapter 3 soon.